Hello everybody and welcome to the Fault2SHA Learning Series. This week I am absolutely delighted to have Rachel Abercrombie with us. She is a research associate professor from Boston University. For those of you who don't know Rachel already, I'm sure you know her work. She's got incredible citations, over 6,000 citations, and an H-index of 40, but more than that, various awards getting her to travel around the world. Her background has got studies from Cambridge University and Reading, and you've had positions at the University of Nevada, the University of Southern California, the Institute of Geological and Nuclear Sciences in Wellington, New Zealand, Harvard University, Boston University, it goes on and on. So I will stop there, but Rachel really has got an incredible experience behind her. And as mentioned today, she's going to be talking about estimating earthquake stress drop resolution and uncertainties. And I know with a lot of us looking at seismic hazard and risk, we really are interested in understanding stress drop, and we use it all the time. So today we've got the best person to explain exactly what it's all about, why is it so difficult to measure, and what are all the uncertainties involved. So Rachel, we're really looking forward to hearing from you today. As always, the point of this learning series is to really help all of us understand different topics, which perhaps we use, we read about, but maybe don't have all that fundamental understanding. So Rachel will hopefully help us along our journey so we can understand all the papers and talks and what we're doing much better. In line with that, Rachel has said it's fine if people would like to interrupt with questions. If there's anything you're not following, please do interrupt or put something in the chat, and we will make sure to address the questions as we go along. And then we hope to have a bit of time for questions at the end. So with that, I say thank you so much to Rachel again for coming. We really appreciate it, and for getting up in the morning to speak to us all. And I hand over to you. So thank you.
Okay, well, thank you very much for coming. So the first scary bit is, can I share the screen? Which is, I think, that one. So hopefully that worked. Yes?
Yes, we see your screen. It's in presenter mode.
Okay. Yeah, okay, super. Well, again, ooh, hang on. Thank you very much for coming.
Rachel, do you want to just flip it so we see just the slides?
Oh, is it not in? Oh, yeah, I see. Now, I don't know how to do that. That's a bit clever. Right, okay, I've got a clever, I know how I can do that. So stop, I'm trying to find the stop share button. That's not, right, where, oh, did that work? Okay, right. So what are you seeing? Okay, try again, share screen. Right, and then is that better?
Yep, we're good to go now. Thank you.
Okay, great. Thank you very much. Well, as you can see, I'm still completely incompetent, even after all these years of Zoom. Anyway, thank you for coming. And what I want to try and do today is to give you a little bit of an understanding of why measuring stress drop is so hard and such a mess, and why you see studies which say stress drop increases with magnitude, decreases with magnitude, doesn't change with magnitude, increases with depth, doesn't change with depth, does change with earthquake location, doesn't change with earthquake location. So essentially, this is really a story of be very careful in any measurements you use of stress drop. And what we're doing about it. And it's also an invitation to you at the end to join an ongoing community study where we are actually trying to improve our measurements and come up possibly with even more useful measurements to people trying to estimate seismic hazard. So, okay, without more ado, I'm going to start off with why we try and measure it and how, why it's so hard, and then what can we resolve. And as you can see, over the years, I've worked with a huge range of people who've all contributed significantly to this work. So basically, as you're probably aware, what you record when the ground starts shaking is a combination or convolution of what comes from the earthquake source, what happens on the way as the waves travel to you, both along the path and also sort of immediately underneath the site. And also, of course, the instrument response. And hopefully these days we know what this is, so we don't worry about it. And I tend to often think of a seismogram as a bit being a sort of set of scales, because it's a balance between what's coming from the source, what's coming from the path, what's coming from the site, the instrument, and whatever we've forgotten. A convolution in the time domain becomes multiplication in the frequency domain, which is why we often work in the frequency domain. And what we're trying to do is separate these things out from the data, so that then we can know what some of them are and we can predict future ground motions. But of course, how do we characterize each one? How do we measure them? And what does it really matter anyway? So one interesting thing I start with is just how we feel earthquakes. So this isn't about the earthquake source at all. This is actually just about the attenuation. And if you look at the map of just where people felt magnitude 6 earthquakes on the west coast and the east coast of the US, you can just see that huge difference in fault areas. And that's telling us that the attenuation, the loss of energy as the waves travel through the earth, is much higher in California than it is on the east coast. Basically, in the newer deforming fractured rocks, the waves don't travel very well, whereas the stronger, older, colder, stable rocks in the east and in Europe, a lot of Europe, ring much more like a non-cracked bell. So obviously, if we're going to be looking at hazard, we've got to do different measurements for attenuation in the east and west. But the other question is, do the earthquake sources differ? So can we just take an earthquake source measurement that we get in California and apply it, and put it in the east coast of the US or into Europe and say this is what the source will be like? Or do we have to actually account for differences in the source itself? And that is what we try and characterize using the term stress drop. And that's what we're struggling to measure. So again, how do we do this? It all derives from work measuring the frequency of seismic waves that was done sort of in the 1960s and 70s by people like Kayaki and Jim Brune and Hiro Kanamori and Raul Madriaga and others. So this was a long time before digital recording and big computers. But what they noticed is that the earthquake source spectrum has a pretty simple shape. If you have a large earthquake, it radiates most of its energy at relatively long wavelengths, and these peak at relatively low frequencies in velocity. As you go to a smaller earthquake, then you get lower, shorter wavelengths corresponding to the smaller dimensions of the earthquake, and a higher frequency at which the energy is peaked. So basically, the frequency at which you get a peak in the energy is inversely related to the size of the earthquake. So if you can measure the peak in the frequency, in the velocity, then you can get an estimate of the dimension of the earthquake. If you convert that from velocity to displacement, it becomes what's known as the corner frequency. You get spectra that look like this. And this again comes from the 1960s and 70s work. And you can see a magnitude 7 will have a relatively low corner frequency, a magnitude 3 will have a much higher one. And they found, Kayaki originally in 1967, that on average, earthquakes scale with this corner frequency value being the equivalent of having a constant stress drop. It scales with the corner frequency cubed scales with the seismic moment. And earthquakes are all much the same. One thing we do here is to turn these dimensions into these corner frequencies into a dimension. We need a value k here, which I'll talk about, but this means that everything we do is somewhat dependent on models, and you have to check that people are actually using the same value for k, because if not, where's my pointer gone, then you really can't compare one thing to another, one study to another. And this is all also assuming simple circular source models. So we talked about attenuation along the path, we talked about the source itself. Another thing to remember is the site effects. And I looked at this back in 1993 and 1995 when I was working in Southern California, and I was looking at trying to get the source out of the seismograms. And we put a seismometer 2.5 kilometers down a borehole, and we also had one at the surface. And we could record earthquakes. So this is an example of spectra from a magnitude 2. And here's the displacement against frequency. And you can see the red is what we recorded down the borehole, and the blue is what we recorded at the surface. And at the low frequencies, we're seeing the near surface amplification As we know, this is what knocks buildings down. But at higher frequency, sort of 1 to 10 hertz, we're seeing the loss of high frequency energy as it travels through the near surface rocks. So as you can see, if you were trying to measure a corner frequency, if you didn't account for site effect, just this last kilometre or so through the Earth, you get a completely wrong answer, which of course would be rather unfortunate. So the model here, I just put it in. This is the basic circular source omega squared Brune model that was really derived back in the 1960s and 70s to fit the basic spectral shape. Moment is the, here we've got an attenuation function on the top, and then 1 over frequency divided by the corner frequency squared. And variations on a theme, omega squared, because we use omega interchangeably with frequency. How do we put all this together? Basically, the simple questions are: you have a seismic moment is defined as the rigidity times the slip times the area. The stress drop, of course, is proportional to the strain, which is the slip divided by the square root of the area. So if we have a length measurement and we have a moment measurement, then basically we can disentangle all of this and get and assume a rigidity and get a slip in an area. So then we can sort of say, well, hang on, what sort of factors control the earthquake source? The stress drop, does it depend on the depth and the normal stress, the strain rate, the temperature, the rheology? If we can measure stress drop, we can see all sorts of things about how earthquake physics works, as well as about predicting the ground motion. We can determine whether they're self-similar. But as you will see from our measurements, it's just not that simple. Again, a reminder for ground motion, why is it so important? If you take 2 earthquakes which have got the same moment here, but one of them has got a long duration and a large fault and a low corner frequency, and one has got a short fault and a high slip over a small area and hence a high corner frequency, same at the long period level, but one has got a higher corner frequency than the other. When you convert displacement into acceleration, same moment coming up here, but now the one with the higher corner frequency has got much higher accelerations and higher damage. So it really does matter quite a lot what value you've got here. So what about the measurements? Well, we've been measuring this for decades, and this is a summary from 2015. There's many more recent ones. Basically what we find is that seismic moment does scale with corner frequency over the approximate, constant stress drop lines here, but there's also quite a lot of variation. I mean, one thing is that there's over 3 orders of magnitude difference here, which is quite a big scatter. And the other is that if you look at individual studies which are combined here, you can see that some of them show distinct trends, which people have argued could be real. Here we're going from magnitude 8, I think, at the top, down to tiny little things in the laboratory. Another method of doing it, this is combining small scale studies, but of course there could be offsets between these. They're coming from different locations. What if stress drop varies with location? Another thing to do is just to look at a single region, in this case Southern California by Peter Shearer, using one massive inversion of a massive data set. But I mean, it looks cool. You can see variation in the color across the region, suggesting variations. But when you look at stress drop against moment, you see this huge range. And you wonder just how much of this is real and how much of it is just scatter. So how can we get at that? Where is it coming from? And the other thing to remember here is I will talk about stress drop, and what I'm really meaning is this multiplication of the moment with the corner frequency cubed. I'm just talking about a sort of moment independent length or scale. This factor K depends on whether you assume a circular model or not, what rupture velocity you use, whether you use Brune's circular model or Boatwright's circular model or Madriaga's circular model. So, it's just a constant factor that can vary by up to about 5. So just take the actual number of megapascals very much with a pinch of salt. Okay, so the first problem then, as I said, is how do we actually go about making these measurements? How do we go about extracting the source from the path and the site and hopefully the instrument? And remember that as we do it, we're always using these simplistic models of circular sources for small earthquakes because we don't have the resolution to do anything else. And in many parts of the world, we only have small earthquakes that we're trying to use to predict the larger ones. And we have to assume that the attenuation is fairly simple as well. But of course, in the real Earth, we know that earthquakes are often complex. They have multiple source time functions, multiple areas of slip, much more complicated looking spectra. And of course, the attenuation in the Earth gets complex, especially at the high frequencies needed to resolve the small earthquakes, which we're having to measure to extrapolate to the bigger ones. So how do we set about doing this? How do we make the measurements? How do we separate it? Well, we either try and model the attenuation, or another method is to use small earthquakes as empirical Green's functions to try and remove the path effects and extract the source. In practice, what we find is that there's a lot of very large trade-offs. And I have recently written a review of this, which I'm very happy to send to anyone who's not able to get the actual journal there, but who wants to know more. I liked this figure from a study by Ko et al. Now 10 years ago, where they just looked at the problem of trying to extract source from seismograms in the frequency domain, where life is a bit simpler to separate source and path. And what they did is they said, hang on, if we take a model which has got the same attenuation, but has different corner frequency values, we get different spectral shapes. That's great, fixed Q, vary corner frequency. But alternatively, we could just put in the same corner frequency and vary the Q, and we'd also get a range of spectral shapes. Now, if we then turn one of these into a model, add a bit of noise, and then try and fit it, what we find is here that if you have a stress drop, attenuation of 0.08 and a corner frequency of 4 in your model, you can then fit it with a curve here in green, which has got a corner frequency 1.5 times higher and a higher attenuation. And really, it's very hard to tell the difference between this green and the black curves. And this is the source of our problems, that we can't tell. Here's the attenuation against corner frequency. Here's where the black curve is, and here's the green. There's just not a lot of difference. There's a lot of trade-offs here. So what we've really been doing in the last 10, 20 years is trying to figure this one out. One thing you can do is we can use clustering of earthquakes and stacking and joint inversion analysis definitely to make improvements on this, but the underlying ambiguities are still to some degree there. The method I've preferred, and you've probably heard of, is the empirical Green's function approach. The empirical Green's function approach means you don't have to worry about modeling the attenuation. You're still putting in a source model, but you don't have to worry about the attenuation. You're basically saying, I've got a little earthquake in the same place as a big earthquake. So the waves from the little earthquake are experiencing exactly the same effects as the waves from the big earthquakes. So we can just remove or deconvolve the little earthquake from the big earthquake, which is a division in the frequency domain, and we get a ratio with 2 corner frequencies, 1 for each earthquake, and that's, magically gives us the corner frequency of the big earthquake. And if we go back to time, we can get a source time function, and we know exactly what was going on. But this requires having a little earthquake in exactly the same place, the same depth, the same focal mechanism, and nicely smaller magnitude than the one we're interested in. And of course, earthquakes often don't behave quite nicely like that, and how similar is good enough, and what if it's not similar, etc., etc. And you end up with quite a limited range of earthquakes that you can do this kind of analysis for, but there again, it's still probably one of the best things we've got. How does it affect things? Grzegorz Kwiatek did quite a nice study of some earthquakes in El Salvador, and they fit the spectra using corner frequency and an exponential expression for attenuation for Q, and they found moment against corner frequency that they got a constant length and a decreasing stress drop as a smaller magnitudes. But if they used an empirical Green's function approach for exactly the same earthquakes, they found now that they were getting more of a constant stress drop. So certainly it matters. We think this is probably doing a better job, but again, there's some uncertainties in there. I did a study a few years ago where I looked at some earthquakes in New Zealand, and here I was curious because we had some nice big sort of magnitude 5-ish earthquakes with their aftershock sequences, some which occurred within the subducting slab here at Upper Hutt and at Eketahuna. You can see the subduction zone here, and these are within the subducting slab. One sequence here, which we actually think happened in the upper plate, and another sequence which possibly happened just about on the slab interface itself. You can see the slight offset from the model and the earthquakes. And I was curious, well, these are pretty distinct tectonic regimes. Can we see differences between them? Because that's really what we're after. And it also gives me a chance to show you some examples of doing the empirical Green's function approach. This is one earthquake at one station, P and S waves. The black is the big earthquake, the red is the waves of the little empirical Green's function earthquake, again for P and S waves. We just take the frequency spectrum of each of these and we get this black and red here, and then the noise spectrum beforehand. If we take the ratio of these two, you get a nice shape with a corner and a corner. And you also, when you come back to the time domain, get a nice source time function. And that sort of convinces me that the deconvolution works and this really is a good Green's function. And then we can try fitting it with omega squared models, and all these different colors correspond to fits, which are shown here for the larger corner frequency. You can see how the corner frequency ranges here and just gives very little variation in the shape of the fit. Then the S wave is much the same thing, and you can see the fits here. So we do this kind of analysis. This is obviously rather a nice earthquake, quite well resolved. And the other thing we can do here that's quite useful, as I said, is measure P and S waves. So we can actually compare the S wave measurement to the P wave measurement. And if we get a good agreement between the P and the S waves, we can say, well, maybe we're right, because what we're after here is confirmation that we're measuring the right thing. And P waves and S waves essentially are independent measurements. So that's a useful thing to look for when you're looking at studies. Did somebody do P and S waves, and did they get the same answer? This was the results of the study that I did for these four regions, coloured in differently. The pink and the red are the ones in the subducting plate. This is the upper plate and lower plate. And the main thing I noticed here is that the stress drop within any individual study, the Eketahuna earthquakes are the best resolved, is much more variation than there is any variation between regions. And this is something we've been finding consistently, that the variation in one location, in one sequence, in one aftershock sequence is much larger than the difference in the average between any different locations. Stress drop really doesn't seem to vary an awful lot with location. I'm just highlighting a couple of earthquakes here, which I want to show you because they are very close to one another, but they have very different values. And I like to go in and say, do I believe this? This is like nearly over a factor of 10 difference. The P and the S waves here, P and S waves here, agreeing quite well, but what do I think? What does the data look like? Well, this is one of those earthquakes, and you can see the ratios, different ratios depending on each different station and different Green's function that I'm using. I use multiple Green's functions for stability, is giving you slightly different ratios, colored for how good I think the Green's function is, and separated that way as well. A lot of scatter, but basically, pretty consistent depending on, regardless of whether I use the best ones or the less well good ones. And the P and the S wave ones are both giving sort of similar-ish values, and, hey, looks quite good. But what about that other earthquake that had a very different stress drop? Well, that's this one here. And you can see it's got a lot more high frequency in it. The corner frequency of all these earthquakes is much higher, of this earthquake is much higher, and the source time function is shorter, implying, I think, that these two earthquakes really are, there's the first one and the second one, significantly different. So I think there's actually something real going on. So I think some of this scatter is real. The other problem, though, we've got is that source complexity is something we've started to realize is going on. We've known for a long time that large earthquakes can be quite complex. They're not just simple circular ruptures. So, for example, this earthquake here, magnitude 7, has two distinct patches of slip, and it has two distinct sub-events in the source time function, and you can see a high frequency bump in the spectrum. The low frequency bump corresponds sort of to the whole area. This high frequency bump is corresponding to the timing and size of the individual sub-events. So obviously, if you're trying to fit this, depending on how you do it and the ratio and amplitude of these, what is this corner frequency that you end up with? Are we just trying to hammer different shapes into a simple circular model? And do we have to bother with this for the small earthquakes, or is this only a feature of large ones? As we've got better and better data for smaller earthquakes, for example, borehole stations or stations on really nice sites on solid rock in Europe and east coast of the US, we find that we're actually seeing complex earthquakes down to much smaller events. So here I looked at 3 sequences that were about a magnitude 2 that were targeted by the deep San Andreas Fault Observatory at depth on the San Andreas Fault in California. And basically it gives us a nice comparison of what you get for some small earthquakes using data from different frequency ranges. So these are showing the earthquakes from 2 sequences, T1, so one example. This is another earthquake from a different repeating sequence, T2, P waves and S waves. And this is from work Annemarie and Ellsworth, who used the SAFOD pilot hole. So these are recordings made at, say, 3 kilometers or so, right by the San Andreas Fault. And they've got data up to, 300 hertz here. So you can really see you've got a nice simple spectrum for T1, but you've got more of a bumpy spectrum here for T2. And even as you go smaller still, you can see bumpier spectra, suggesting we've still got complexity down to these much smaller magnitudes. I used the shallow borehole network data, did the same thing as before, all of these spectral ratios again, simple source time functions. This is for the T1 earthquake. Now I've now got a lower frequency range. I've only got this frequency range here because I'm using shallower data. But again, this is fairly well resolved. You can see it here. I get basically the same answer. Nice and simple. Kim et al. From Berkeley, again, nice simple circular rupture when they tried to do a finite fault inversion for it. However, T2, this earthquake here, just next to it, you can see bumpier spectrum here. I'm also seeing bumpier spectra. Depending on how combination of EGFs, I get different amplitudes for this high frequency bit, which changes the corner frequency I measure. And you can see that we're seeing complexity in the source time function, which really shows up when you look at the source time functions with azimuth for different stations. You can see the double pulses. Now, obviously, this is going to give me a different answer depending on the frequency range that I have. And if I only had surface data, I would only be up to frequencies of about, say, 20 or 30 hertz in this region. And now I'm really just not going to see that complexity at all. And I'm going to completely misestimate the value that I have. So frequency range is a real problem when we have complex earthquakes. Another example that I recently published on was to look at a magnitude 2.7 repeating sequence of earthquakes at Parkfield. Again, these very similar waveforms. These are the source time functions after correcting for empirical Green's function analysis at different stations. And you can see that there's significant variation in duration of these source time functions with azimuth, which is consistent with directivity of rupture. And you can see the multiple pulses quite nicely, and the same for all of these repeating earthquakes, suggesting they're very, very similar, suggesting that they're rupturing along the San Andreas Fault to the northwest. But also showing complexity even down to small earthquakes. So our circular sources are always going to be an oversimplification. So that's been talking to you about what we can do with empirical Green's functions, which tends to be studying small numbers of well-recorded earthquakes. Another approach which has become popular is this sort of large-scale inversion of large numbers of data recorded at large numbers of stations. So, for example, work done by Peter Shearer's group and also Dino Bindi in Europe is another one. And this is very similar to the large-scale inversions that are used by people to estimate attenuation or to get at side effects. Basically, you take a lot of earthquakes recorded at a lot of stations and you try and divide it all up so that there's a bit that's basically the same for each event, an event term. So that's the same regardless of which station it's recorded at. You have a station term, and that's a bit which is, you know, distinct. All earthquakes will have the same answer at each station. And then you have a travel time term, which is basically how long do the waves travel through the earth, and that will give you an attenuation. And you can do this in a stacking method, which is what Peter Shearer's group did, and this is just showing you the spectra stacked in different magnitude ranges. Or I think here, this is how many events are actually in the stack at each magnitude. The main thing that happens in most of these studies is that the attenuation Q just depends on the travel time. So they're assuming that there isn't any sort of real spatial variation or depth variation in attenuation. So again, what we've been finding out in recent years is that there's more ambiguity here than we would like. So this is the data that comes out of that inversion for the event terms that Peter Shearer got for, this was work at Lander's sequence in California. And then what you have to do is you have to put in some kind of global correction for essentially site effects, a global empirical Green's function or a correction spectrum to actually turn these into source spectra. And the assumption that he uses is that they have a Brune source model of some sort. Now, what we tried to do is we tried to fit them, making different assumptions about that source model. One assumption is that they're all just a Brune source model, but that the stress drop varies, you know, can vary from a low value to a high value with magnitude. Another is to force the stress drop to be the same for all magnitudes. Another is to force it all to be the same, but change the fall off rate here of the spectrum a little bit from this common 2 to a smaller value. Or alternatively, let's force them all to have a low stress drop or a high stress drop. And the main thing you notice here is that the dashed lines, which are the fits, look awfully like the solid lines in every case. We've got a different global Green's function, but really I wouldn't like to pick which of these is fitting the data better, which is basically telling us that this is an ambiguous problem and we are, you know, we're not sure. This is why different studies give us different answers, because the data are ambiguous. Another question I've been looking at recently is revisiting does stress drop increase with depth? Which of course, you know, does the deeper earthquake radiate more high frequency radiation than a shallow earthquake and knock buildings down better? Or from the earthquake source problem, is the actual stress drop related to the stress in the earth? As you go down, we think that the rocks get harder to break because you've got more normal stress. So brittle failure will get harder until, you know, things become aseismic with the increased depth. And we certainly see that seismicity, you know, varies with depth, and people have tried to relate this to the rock type and et cetera, et cetera. So, you know, how does that work? Well, some of these large-scale inversions by Daniel Trugman, Peter Shearer, Jean Hardybeck, and others, also you know, Bindi, Adrian Oath in Europe, have actually found for different regions that they've looked at that the stress drop here maybe varies with moment. This may or may not be right, and also varies with stress drop. Stress drop varies with depth in some of these regions. Also seen for the Hayward fault, blues going down to reds. And I was curious whether this was real or whether it could possibly be some kind of artifact and how we would tell. So I contacted all of these people and worked with them, and we revisited all the spectra, over 50,000 events that these people had studied in these different regions of California and Oklahoma. And what we found is that, yes, the source spectra have more high frequency energy. Well, no, the spectra, the recorder spectra, have more high frequency energy when they are deeper than when they're shallower. So this is basically showing the ratios of the low frequency energy to the high frequency energy. Get this right, high to low, sorry, as a function of depth in each of these different regions over here. And all of them, you can see there's a slight increase with depth, suggesting that, you know, there's something going on. Now that would be consistent with stress drop increasing with depth, but it would also be consistent with Q increasing with depth. So I looked at the question of doing the sort of large scale analysis versus the empirical Green's function analysis to see what would we expect and can we use that to constrain what's going on here. So what is happening in these large scale analyses is basically we're saying you have big earthquakes and little earthquakes at different depths recorded at stations, and you can use all little earthquakes in a region regardless of depth anywhere near to correct essentially for the attenuation along the path. You're just doing it as a time dependent path effect. But what about if the large earthquake is shallow and the little earthquake is shallow and they have a slightly different path to the large deep and the shallow deep? You know, what if we make that correction? So to do this, I made some theoretical curves, and that's sort of shown here. So these are spectra if the stress drop is constant, but Q increases with depth. So that's this situation down here. The spectra of a big earthquake that's deep would be this dark blue one here, and a little earthquake that's deep would be the dark blue one there. The big earthquake that's shallow here, less high frequency energy in the spectrum because it's been attenuated more because it's traveling through these shallower rocks. Again, same for the smaller earthquakes. I also calculate the average of these two little earthquakes because in this situation here, I'm basically using the average to correct. If I then do the spectral ratios, if I do the spectral ratio of the large, deep to the average, I get this dark red here. If I do the spectral ratio of the shallow, large to the average, I get this orange here. And they're different, of course, because these two are different and I'm dividing them by the same thing. But if I take the deep one, large one, and divide it by the deep little one, and the shallow big one and divide it by the shallow little one, the differences disappear because all the differences in this model were coming from the attenuation. So basically what I can do is I can go back to the data here and I can take the big shallow ones and divide them by the little shallow ones and the big deep ones and divide them by the little deep ones and compare them to dividing the big of each by all of the shallows and see whether it makes any difference. Alternatively, if stress drop increasing with depth and Q is constant, then we have the different shapes again, but now we're not really seeing anything different happening when we do the correction for a different attenuation because, well, it's the same for all the paths, so it doesn't make any difference. If we've got a bit of each going on, then the difference between the deep and the shallow decreases as we make the correction, but it doesn't disappear entirely. So what happens when we do this with the data? This is the Ridgecrest earthquake sequence in California. And again, just same coloring. If we take the shallow large and divide it by the mean of the small and the deep large divided by the mean of the small, we get dark red and orange in different magnitude ratios and different, this is stacking earthquakes, everything in this magnitude range divided by everything in this magnitude range. If we make the correction for the depth dependent source, small earthquakes, a lot of that difference disappears. The two red curves are nearly always more apart from the two blue curves, suggesting it's more like this case. Could be this one because it doesn't disappear entirely, but it's probably not this case here. So essentially, some of this difference with depth is not source, it is attenuation. And we can do this for all the different ratios. So this is showing the curve. So this is now this red curve divided by this red curve, this blue one by this blue one. The blue ones are flat because we've got rid of the difference in attenuation. And the red ones are different because, we've still got the attenuation problem in. This is Ridgecrest. So this is all these red curves here divided and these blue curves divided. And then these are some of the other regions that I looked at, Landers, Parkfield, Hector Mine, I think. No, that's Haywood, that's right. And you can see that often the reds are different and then the blues are essentially the same. And what happened is in every case, when we do the mean of this amplitude deep over shallow, the red is always higher and it pretty much always decreases down. Different points are different magnitude bins. They should all be the same. There's no reason why this should be different for magnitude. So this variability here between magnitudes is telling you something about the uncertainties. But I think what we are seeing here consistently is that some of the source difference in the previous studies is most definitely coming from problems with attenuation. And it's at this point that I'm realizing that I've got far too many slides, so I'm not going to be able to talk about everything I wanted to. So I'm going to try and just give you a couple of highlights from what's left. And then you can look at papers or ask me questions about it if you want to do so. The last one on this subject is basically just saying the same thing again, which is that if you don't do any kind of depth correction and you do the deep divided by the shallow corner frequencies, you can get a relationship which is different from 1 depending on the velocity of the rocks. But if you do the correction, these numbers all decrease down and come down to being consistent with no significant variation in stress drop with depth. There could well be some there, it's just we're struggling to resolve it. This is just to highlight some work done in Oklahoma, the Prague earthquake, one of these induced events in the US. And Colin Pennington, for his thesis with Xiaowei Chen, performed multiple studies using different methods of the same earthquake. So all of these are different ways of measuring the stress drop for these set of earthquakes, stress drop by study type. And you can see that the average is varying quite a lot. But what you also see is that for each earthquake, this is just plotting individual earthquake corner frequency here against an alternative method. And for all of them, you're actually seeing some sort of correlation. So lot of variation, but definitely some correlation as well. Some of this is real and some of it is not. Stress drop estimates, on the whole, the earthquakes at a high stress drop in one study, a high stress drop in the other. The absolute values vary an awful lot, but it's not just random. And then that's shown again here. He finds that one particular fault, the aftershock fault, actually had a slightly higher mean stress drop in blue here than the estimates for the other faults. And that was consistent regardless of which method you used. So look for people who do you get the same results from consistent studies? Do you get the same answer from different people looking at the same data using different methods? If so, be more inclined to believe it. The last study is some work that I have currently in press, looking at the, not in press, in review, to be honest here, looking at the Italian sequence of earthquakes in 2016, where we had the damaging magnitude 6s and some aftershocks, and quite complex slip distributions were worked on by other people. And I used this sequence as an opportunity to compare the spectral methods with the finite fault inversions, because Lisa Tinti had calculated finite fault inversions for these. Various people have shown the possibility of the stress drop, there we go, increasing with magnitude for these, but maybe constant here, maybe increasing here, maybe this is a resolution problem, maybe this is real, maybe it's not. This is somebody else's, Paolo Marasca's results for the same earthquakes. What Giovanna and I did was, again, we used ratio methods, displacement spectra, etc., multiple methods to try and measure these results for the same earthquakes. And we then compared our measurements. The ratios, the red, the yellow is her fitting, and the blue is Dino Bini's large-scale spectral inversion. And we found basically these are the stress drops against magnitude. There's differences, and the error bars are shown here. So the error bars are clearly too small because everybody's measurements doesn't fit within everyone else's error bars. But there are also systematic consistencies here, patterns here with an increase in stress drop, maybe a down and up. And all of them are showing the same relationship, a low stress drop for Viso, a high for Amatrice. And to just trundle through this, you can compare the measurements we get with the slip distribution for these earthquakes and basically find that the Amatrice earthquake has got a lot of complexity, a low peak slip and high and stress release, whereas Viso is the one which is simpler with a higher peak slip and stress release, but you end up with a higher corner frequency and a higher Brunstyle stress drop for Amatrice because the complexity is adding to the high frequency content of the waveforms. And that's just shown here. Amatrice Spectra has got more high frequency energy than the Viso. So in terms of studying, using this stress drop value we measure to look at the actual stress release on the fault, it's not very good, but maybe this Bruhn stress drop is better and more reliable for ground motion prediction, because it is saying, you know, this is predicting whatever this number is, it's predicting more high frequency ground motion, which is what was actually resolved. So finally, what's happening at the moment to try and resolve these questions is I'm involved with Annemarie Baltay in organising a Southern California Earthquake Center community stress drop validation project. The web page is here, and I'm going to get Joanna to share it with you, because I would invite any of you who is interested at all to join us. It's basically a coordinated community effort to try and do something about this mess that we find ourselves in. How can we make measurements which are actually, you know, reliable and useful and meaningful, and how can we communicate to the community what does this stress drop actually mean? What you measure is, you know, very different in a ground motion study to if you're trying to do details of complex earthquake source physics rupture modeling, dynamic rupture modeling. We're inviting the community to make estimates of stress drop for a 2-week data set of earthquakes at Ridgecrest. And the idea is that we can make measurements, compare them, look at the differences, recalculate and repeat, but also that we share those results with the people who use them, so that you understand where they're coming from. So joining this group doesn't mean you have to make any measurements. You can just be interested to see the results. We had over 100 people come to our first virtual workshop in November last year. And if you join our mailing list, you won't get that many emails, but you will at least sort of have, you know, what's going on and be invited to join future workshops. We should have another one coming up, virtual one, later this year. These were our preliminary results. Now, it should be mentioned that these results from 11 groups submitted 14 different measurements. These were really preliminary. People did these in a tearing hurry. They're not fully quality controlled. So, you know, things will get a bit better, but they do demonstrate the problems we've got. These are the measurements we have of stress drop against magnitude. These are all the studies. This is the difference between the moment magnitudes people estimate and the catalogue magnitudes, and these are the corner frequencies people estimate. If you just do the large scale inversions only, that's all the greenish ones are plotted here, and the improvement Green's function studies are plotted here. You can see the huge variations. You can also see distinct trade-offs here between like the turquoise ones and the yellowy ones and the dark blue ones. You know, this is higher than this one, and then you've got the trade-off down here. You can clearly see trade-offs happening between moment and corner frequency, giving different stress drops. So somehow or other, each of these earthquakes only had one moment and one average stress drop, and we're not quite there yet. So in conclusion, I guess I would like to say, interpret stress drop measurements with care. I have a recent review out, which, as I said, I'm happy to email anybody who is not able to find that easily. But basically, we're getting real uncertainties from the limited quantity and quality that we've got for the small earthquakes that we need in the various regions where there haven't been any large ones that we can use to measure hazard. We're struggling with simplifying assumptions about the attenuation in the source model. We're working to improve these. We're trying to work out, you know, can we get best average values from systematic analysis of lower quality data, which we can use for hazard, and also what can we do with detailed analysis of the best recorded events. But for now, I would say relative values are much better than absolute. Temporal and spatial variation, I think, is being observed, but make sure you've got multiple methods giving you consistent results before you believe them. And I guess from the hazard point of view, I'd say that if you get this balance all wrong, but are interpolating, it won't really matter, because the things will trade off against one another and they will do it as you predict as well as you make the measurements. However, if you're trying to extrapolate measurements well outside the magnitude range of which you have the data, then getting this balance slightly wrong can lead to large problems in your measurements. So finally, if you do want to know more and keep up with the work, then come and join our community study. So that's all. Thank you very much.
Rachel, thank you so much, and also for that last slide, for the advice for everyone going forward and how to use all this. We have just a couple of minutes, so would anyone like to ask a question? Either post it in the chat or just ask aloud, that's fine. Would anyone like to get some last moment of wisdom?
Oh dear, I always just say too much, so I know everyone.
No, it's fantastic, because it's a chance to actually really, go into it and understand why we get all these different results and where they're all coming from. It was interesting what you just were speaking about then, about it being the relative results which are so important. And does that sort of stay with different scales, or is that very much within magnitude ranges? Because you also talked about extrapolation and how that gets very difficult if you haven't got the data outside those magnitude ranges.
Yes, I mean, the problem is, of course, if you put in a moment increasing, a stress drop increasing with moment, and attenuation doing something else, and as long as you stay within your interpolating, those will cancel out and it won't really matter. But of course, extrapolating, you'll go way out. The relative measurements, I think, is just the fact that we measure stress drop in megapascals, but as I said, depending on what you assume about the rupture velocity in your circular model, and this person's model and that person's model, you can get factors of 5 difference easily just from the simple factor you're putting there. So don't look at a paper and go, oh, they said 10 megapascals and oh, they said 1 megapascal. Look at them and think, well, which model did they use? And maybe actually, it's more going to be that they found that these earthquakes have slightly higher stress drop than those. But the other problem, of course, is that the moment dependence tends to come out of the limited bandwidth of each study. So there is definitely a tendency to overestimate the stress drop of the largest earthquakes and underestimate the stress drop of the smallest earthquakes in any analysis, which tends to give you this increase in stress drop, which sometimes goes away if you have a larger bandwidth.
And that becomes critical for hazard analyses, actually. So that's unfortunately
yes, exactly. This is really serious, and I think one of the funniest things I did was that big reanalysis of the the 50,000 earthquakes to look at the stress drop and depth, just going back with each of those co-authors and then zooming with each one and saying, well, I re-looked at your data and I get a different answer. What do you think? And we all realized that maybe it's not as well constrained as we'd hoped. There could be depth dependence. There probably is some depth dependence, but it's definitely not as big and not as widespread as the original studies suggested.
So more work to do then, as always.
Exactly. So like I said, come and join us. We've got, I'll send you the website. There's actually some videos online there of people talking about, what they use stress drop for, what might be better. And we're actively working on this and meeting regularly. And we'd love, anyone who wants to know more about it, please come and join us.
Rachel, thank you so much. I really appreciate your talk and your time. And as I say, getting up earlier and everything you've had to say. So Rachel, thank you so much. And thank you to everyone for attending throughout the series. We're going to have a break in August so that people can have a holiday, and then we'll start again in the autumn. So I look forward to seeing you all again then. So thank you again, Rachel, and everyone for attending, and see you all soon.